On page 285, we have the mean value theorem for integrals. Hush. In section 4.2, you saw that the area of a region under a curve is greater than the area of an inscribed rectangle and less than the area of a circumscribed rectangle. So if we look at the screen here, the red rectangle would be inscribed. Well, obviously the area under the graph of f of x between a and b is greater than the area of that red rectangle. The blue rectangle is the circumscribed one. Well, it's also kind of obvious that the area underneath f of x between a and b is less than that. So the mean value theorem for integrals states that somewhere between the inscribed and circumscribed rectangles, there's a rectangle whose area is precisely equal to the area of the region under the curve. So I made that one the black rectangle. Okay? I mean, it kind of stands to reason, right? If the area of the region is between, numerically, between the area of the red one and the area of the blue one, shouldn't there be a rectangle between the red one and the blue one that has that precise area that we're looking for? Okay? So here's what it says in Mathese. It says, if f is continuous on the closed interval from a to b, then there exists a number c in the closed interval from a to b, such that the integral from a to b of f of x dx, which, since in this case, in this drawing at least, f of x is above the x-axis, that's the area, and even if it were below, it'd be the signed area of the region, equals f of c times the quantity b minus a. Well, where's all this come from? Well, b minus a, if the interval of our region goes from a to b, isn't b minus a the base of that, in this case, black rectangle? F of c. C is, c is what we don't know. It's in there somewhere between a and b, but its height, if the x-coordinate is c, then that y-coordinate there would be f of c. Well, that would be the height of that black rectangle. So C is the point where, C is the x-coordinate that gives you the correct height to get that area. Okay? Does that make sense? We will be finding C. Okay? So, that's all a big area, isn't it? Now, if it's below the x-axis, it can be signed area. And then, of course, we got to worry about some below, some above. So, that's why they didn't put that on the theorem. Okay? But that integral equals that, base times height. You with me? Okay. And then it says, note that the theorem does not specify how to determine C. It just guarantees that it exists. All right? Yeah, it's nice to have guarantees. Not many guarantees in life. Like, for instance, there's no guarantee that you'll understand number 43. But we'll try it anyway. I'm on page 291. Good old page 291. Number 43. Find the value or values, because there could be, depending on what the shape of f of x is, more than one place where you get that rectangle. Find the value or values of c guaranteed by the mean value theorem for integrals for the function over the given interval. So on 43, our f of x is x minus 2 times the square root of x, and our interval is from 0 to 2. The mean value theorem for integrals says that the integral from a to b of f of x dx equals f of c times the quantity b minus a. We know everything except c. All right? Well, I'll take that back. We don't know x. All right, so our integral from a to b of f of x dx. What's a? 0. What's b? So that becomes the integral from 0 to 2. We do know f of x. It's x minus 2 radical x dx. All right, so filling in the left side, not so bad. On the right side, we know f of c. We don't know what c is, but if f of x is x minus 2 radical x, isn't f of c c minus 2 radical c times the quantity b minus a? So times the quantity 2 minus 0. Now, I originally said, well, we know everything except c, then I backtracked and, well, we don't know what x is. Do we even need to know what x is? No, because we're going to find that definite integral. The left side's going to be a number, isn't it? And so then we will just have one unknown. And for the most part, as long as we just have one unknown, we can solve for it. So let's concentrate on the left side for a minute, and let's evaluate that definite integral. According to the fundamental theorem of calculus, the way to evaluate the integral from a to b of f of x dx is to find the antiderivative of f of x and evaluate it from a to b. So we're going to find this. We're going to find the antiderivative, and we're going to evaluate it from 0 to 2. So the antiderivative of x is 1/2 x squared. Now that 2 radical x, think of that as 2 times x to the 1/2, and then power rule the thing. So you add 1 to the exponent, make it a 3/2. Then you divide your coefficient of -2 by 3/2. Or better yet, you multiply your coefficient of -2 by 2/3. So we get -4/3 x to the 3/2 evaluated from 0 to 2. Correct. That's when we no longer need the dx in our notation. Now, on the right side, all I did was put the coefficient of 2 in front of the c minus 2 radical c. Back to the left side. Now we do the evaluating. So now we're to the stage where we need to do capital F of, in this case, 2 minus capital F of 0. It's capital F of b minus capital F of a. So we evaluate our antiderivative for 2. That's what I have underlined in blue. Put a minus sign, and we evaluate our antiderivative for 0. That's what I have underlined in red. And it's arithmetic from here on out on the left side. All right, so what I've got underlined in blue there, when you square the 2, you get 4. Half of 4 is 2. And then that 2 to the 3/2, all right, that's tough to deal with, because if I cube that first and then take its square root, that'd be the square root of 8, right? And I'd be really, I'm kind of okay with you just writing the square root of 8. But the square root of 8 is simplified to be 2 radical 2. So there's not a real good thing to do with that, is there? Okay, so the best we can do with it is call that -4/3 times 2 radical 2. Haven't messed with the right side in a while, have I? All right, now, you tell me how I got that. Now, I divided both sides, or it actually works a little better if you think of it as multiplying both sides by 1/2. Because that way I can distribute. You don't technically distribute division. We know what we mean, but you don't. So I multiplied both sides by 1/2. Why would I do that? I mean, it just simplified it just a bit. because 1/2 times 2 is 1. All right. Now, if you don't do that step, is that okay? Yeah, it's fine. All I did was just reduce the numbers just a bit. All right. Now, we need to try to solve this thing for C. Let's, if we subtract 1 from both sides and add 4/3 radical 2 to both sides, we get that. All right, now, a couple reasons I did that. One, I can solve this on my calculator now. Okay. Two, believe it or not, I can solve that like a quadratic. Instead of an x squared and an x, I have a c and the square root of c. But you see how that correlates to being the same thing? If you let let's might as well call it u. If you let u equal the square root of c, couldn't you rewrite that as 0 equals u squared minus 2u and then plus? And I could actually solve this with the quadratic formula, in theory. Okay, I'm not sure I could do the arithmetic right. I didn't square anything. I just did a substitution. When I noticed that that number, the c, is that one squared, well, I can treat it as a quadratic. If u equals the square root of c, isn't the square root of c squared c? That's where the u squared comes from. That square root of c is now called u. That didn't change. All right, but let's do this on our calculator if we can. So we get our calculator. All right, so let's let our function be, and I'm going to call it x because that's what I have on my calculator, x minus 2 square root of x, close that parentheses, minus 1 plus parentheses 4/3, close that parentheses, square root of 2. I'm fairly sure I have it typed in my calculator correctly. Let's graph that thing. All right, now, I really just want the graph from 0 to 2. So how about if I'll just zoom, I'll zoom decimal first and see if that helps. It helps enough for me to see that I'm going to have 2 different answers. Do you see there's going to be 2 different answers? See how the graph starts out above the x-axis, dips below, then comes back above? So there's 2 answers. All right, so let's find them. Let's do second calc. Let's find the zeros. So that's number 2 for me. I'm going to find the one on the left here first. So I'm going to cursor over close to that. Notice my y-coordinate's still positive, so I'm still above the x-axis. I'll let that be the left bound. I'm going to cursor a little more. Now my y is negative, so I've crossed over to the other side. I'll hit enter there. I'll back up a space for my guess. And I get x to be about 0.437974, or about 0.438. The AP people always want it to 3 decimal places. They won't even look at the rest of them, so there's no need for you to have your... Now, as you're working a problem, keep all your digits. But as an answer, the first 3 is all they look at. Okay? And now let's find the other one. So, oops, I need to do second calc again. I need to cursor over there closer to the second one. Still y is negative. Go over there to where y is positive. That'll be my right bound. Back up a couple. That'll be my guess. And I get about 1.79078898, or about 1.791. And that's how you find the C that makes the mean value theorem for integrals work. So what that means is that when C equals either of these, it gives you the correct f of C to multiply times the base of the rectangle, which would be 2, to get the same as the area underneath the graph of x minus 2 radical x. Right. It will be the same rectangle because it will give you the same height. It's just you can get that correct. I say correct. You can get the height you want using two different x's. We did, and we found that no, we didn't solve for the height. We solved for the x coordinate that leads to the height. Okay. We would have to plug those back into this to find those heights. Well, and it'd be the same height. All right. Y'all with me on what we did and what we found? All right. Now, the average value of a function is a definition. It says the value of f of c given in the mean value theorem for integrals is called the average value of the function on that interval from a to b. So they didn't ask us to do it here. But if we find what f of 0.438 equals, or what f of 1.791 equals, they'll be the same. That's the average value of this function, x minus 2 radical x, on this interval from 0 to 2. Now, our definition gives us this little formula. It says if f is integrable, in other words, you can find its integral, on the closed interval from a to b, then the average value of f on the interval is, and then where on earth did they find this formula? If it's f of c, how come that's the formula to find it? That's what the mean value theorem for integrals says, correct? Yeah. Just multiply it by 1 over b minus a. So you get f of c alone, and what's on the other side? That. It's just rewritten. Now, if I had been in charge, and I'm not, I would have written the definition out like that. So, the rectangle that has the exact same area as the region, the height of that rectangle is called the average value of the function. Y'all with me? The rectangle that has the exact same area as the region has, its height is the average value of that function. Now, talking about any of this on anything other than a closed interval doesn't make any sense, does it? We don't have areas unless we have closed intervals. So all of that's on the interval from a to b. Question? All right. Well, let's see what they want us to do with this newfound knowledge. So, number 48. Still on page 291. Find the average value of the function over the given interval and all values of x in the interval for which the function equals its average value. On number 48, they give us that f of x equals 4 times the quantity x squared plus 1, all that divided by x squared. And the interval they give us is from 1 to 3. Now, we're supposed to do two things. We're supposed to find the average value, and we're supposed to find all the x coordinates for which it occurs. All right? So let's find the average value using the formula, the definition that we have. The average value, f of c, equals 1 over b minus a times the integral from a to b of f of x dx. Yes? No. I don't know why they don't. Unless they just don't want you to get caught up thinking that the only way to write it is f of c. I mean, instead of writing f of c, I could have just written, you know, average value equals, okay? All right, so that's our definition of the average value, no matter what we call it. That's the definition of the average value. So let's fill everything in that we know. Okay, we've got 1 over b minus a. Well, a is 1, b is 3, correct? So our average value equals 1 over 3 minus 1. Then we have the integral from a to b, so the integral from 1 to 3, of f of x, which they told us is 4 times the quantity x squared plus 1 all over x squared dx. So we're going to have to be able to find this definite integral to find the average value. So we've got 1 over 2 times. And then you can see here, at least I can on mine, where I erased. Looks like I decided, oh, I can factor out that 4, right? Since a definite integral is the limit of a sum. Remember the definition? I can factor constants out of sums. I can factor constants out of limits. I can factor constants out of integrals. Am I required to factor constants out of integrals? No, I'm not. It's usually a good idea because it makes the arithmetic that we have to do to get the definite integral easier, usually. Can't say always, but usually. Okay? So I factored the 4 out in front, times the integral from 1 to 3. And then look, so then I've got this integral still. I can't evaluate that. There is no quotient rule for integration. So how did I get 1 plus x to the negative 2? Well, actually, I don't think anybody said what I actually did. Yeah, I just did the division. I divided x squared by x squared, and then I divided 1 by x squared, which is the same thing as multiplying by x to the negative 2 over x to the negative 2, which somebody did say. Okay? So x squared divided by x squared gives me the 1. And then 1 divided by x squared, I mean, it's still 1 divided by x squared. But change its notation so that you can use the power rule for integration on it. All right? Now, according to the fundamental theorem of calculus, that definite integral is going to be the antiderivative evaluated from 1 to 3. It's going to be the antiderivative evaluated to 3 minus the antiderivative evaluated for 1. So it's going to be integral sign, 1/2 times 4 is 2. And now, what's the antiderivative? Well, the antiderivative of 1 is x. The antiderivative of x to the negative 2, follow me here, x to the negative 2, add 1, divide the coefficient by the new exponent, and so that's a negative 1 over x, isn't it? So that's what I wrote, negative 1 over x. Evaluated from 1 to 3. Which first, the 3 or the 1? The 3. So we got the 2 out in front. Substitute the 3 in to your antiderivative. Put a minus sign. And substitute the 1 into the antiderivative. You could. Yeah. At any point, we can multiply that 2 by. If you see a bunch of 1/2s in there, then I'd go ahead and multiply by 2 and get rid of the 1/2. So we've got 2 out in front. Now our second parenthesis is 1 minus 1, so that's 0. So then 3 minus 1/3, that's 9/3 minus 1/3, that's 8/3. 2 times 8/3 is 16/3. So f of c was what we called this originally, or average value. Well, label it either way, both ways. All right, it's 16/3. Now, before we actually find the places where we get this average value, remember that means that the height of the rectangle that's the same, let me rephrase this. The rectangle that has the same area as the region has a height of 16/3. That's the y value. Right. You got that. You got that. Well, that's obviously too big, but whatever c is, that y value is 16/3. Okay? All right. Next, they want us to find the x-coordinates that lead us to this average value. Well, so that means we want our function to equal its average value, right? Set the function, and I used c. You can leave it with x's. I don't really care. But take that function and set it equal to its average value. Then it's algebra. All right, so I just did cross products to get 12 times the quantity c squared plus 1 equals 16c squared. I distributed the 12. I could have divided both sides by 4 right there if I wanted to. I didn't think of it. I distributed the 12. I've got a quadratic, so I need to get it in standard form. So I subtracted 12c squared and 12 both sides. I can solve this one by factoring. So I factor. Now, we don't usually think of c squared minus 3 as being a difference of 2 squares because you don't think of 3 as being a square, but it is. 3 is the square of the square root. So I left out a step saying this. All right, and now, are they both in the interval? What's our interval? 1 to 3. So in the interval from 1 to 3, c equals square root of 3. I'll pass. All right, we're doing okay? Number 68. All right, we get to turn over to page 292 now. Ooh, 293 actually. It says, have we already done this one? No. It says find capital F as a function of x and evaluate it at x equals 2 and 5 and 8. Well, it's not the second fundamental theorem of calculus because they're not asking us to find its derivative. Okay? The second fundamental theorem of calculus would be to find capital F prime of x, which would be x cubed plus 2x minus 2, right? But that's not what they ask us to do. So, find capital F as a function of x. Right now, capital F is a function of a definite integral. Well, let's simplify that definite integral. So find the antiderivative, evaluate it from 2 to x. First we evaluate for x, then we put a minus sign, then we evaluate for 2. So capital F of x equals 1/4 x to the 4th plus x squared minus 2x minus, and then when you get finished simplifying everything in that parentheses, it's a 4. All we did, we used the first fundamental theorem of calculus to come up with this. Now that we have f of x written as a function of x, we can evaluate. Because remember what the alternative would have been? The alternative would have been to put a 2 there, figure out what that definite integral is, which would be easy. Then to put a 5 there, figure out what that definite integral is. And then put an 8 there and figure out what that definite integral is. So, Right, so we just gave ourselves an equation, a formula, instead of having to find the definite integral 3 different times. Okay? So, finding it for 2, and really, you ought to know what the answer is going to be, right? Because what would the integral from 2 to 2 of whatever? It's got to be 0. So when we evaluate this, when we put a 2 in for x, we'd better get 0. And we do. And feel free to use your calculator for these. What do you get for capital F of 5? That's what I got. And what do you get for capital F of 8? $1,068. That's what I got. All right. We've only got one more example to do, and we need to pick up the pace a little bit. So number 74. Let g of x equal the integral from 0 to x of f of t dt, where f is a function whose graph is shown. They want us to estimate g of 0, g of 2, g of 4, g of 6, g of 8, and then we'll answer the other questions. All right, so we can't do this one like we just did the 68 because they don't tell us what the equation that goes with the function is. Okay? If they did, we could have, right? We're not going to guess. We can count squares. Okay? So, we're supposed to figure out what g of 0 equals. Well, g of 0 would equal, well, replace in your g of x equals the integral from 0 to x, replace the x with 0. So we have the definite integral from 0 to 0 of f of t dt. We have a property from a long time ago, even though it was in this chapter, but it's from a long time ago that says the integral from a to a of f of x dx equals 0. So the integral from 0 to 0 of f of t dt equals 0. All right? The integral from 0, or g of 2 then, will equal the integral from 0 to 2 of f of t dt. Well, from 0 to 2, that region's completely below the x-axis, so we will get a negative signed area for this definite integral, won't we? All right? And that region is in the shape of a triangle. So 1/2 base times height will give us this definite integral. You with me? All right, so we got 1/2 base times height. Now, you've got two options on where to put the negative. You can just say, hey, that whole region is below the x-axis, so I'm going to just call it negative 1/2 base times height. Or, equivalently, you can say 1/2 times the base, and then give it a negative height since the f of c is negative. Either way is perfectly correct. Don't do both. Because if you do both, then you'll have two negatives, and a negative times a negative, you'll end up with a positive signed area when you're supposed to end up with a negative signed area. So negative 4 then we find g of 4. G of 4 is going to equal the integral from 0 to 4. So again, it's a triangle. It has the same height as the previous one did. Its base is just twice as big. So what do you get for the integral from 0 to 4? Negative 8. All right. Next, we find the integral from 0 to 6. Now, can't we divide our definite integral up into any integrals we want? Any of them that are useful to us? So let's think of this as the integral from 0 to 4 plus the integral from 4 to 6. We know what the integral from 0 to 4 is. It's negative 8. So we just have to figure out that. Actually, it's not a triangle. It's a trapezoid. So you can. So we've got the integral from 0 to 4, that's negative 8, plus the integral from 4 to 6, which, since I'm treating it as a trapezoid, that's 1/2 times the height times the sum of the bases. The bases are the parallel sides. So the height would be that. One of the bases is that. The other base is that. So 1/2 times a height of 4 times the sum of a base of 1 plus a base of 2. Which gives me negative 2 when I'm done. And then, the very last one, they want to know the integral from 0 to 8. How are you going to break that one up? I'm breaking it up this way. I know what the integral from 0 to 6 is. It's negative 2. So then plus the integral from 6 to 8, and that's the exact same as the trapezoid we just got through doing, right? So if I think of this as the integral from 0 to 6, which is negative 2, plus the integral from 6 to 8, which will be 1/2 times 4 times the quantity 1 plus 2, what do you get? 4. And now they ask us some nice questions. All right, let's see. I've lost it from the book. Yeah, find the largest open interval in which f is increasing, and then find the largest open interval. I said f. G is increasing, and then the largest open interval in which g is decreasing. All right, now this is the graph of f, not the graph of g. But look, we have values for g, don't we? What are the values of g doing there? They're decreasing. What are the values of g doing here? They're increasing. So we can answer it from the numbers that way. But then also, let's tie all this back in. G is defined to be the integral of f. Doesn't that mean that f is the what of g? Well, let's just think of it as g and f. If g is the integral of f, f is the derivative of g, right? If g is the antiderivative of f, f's the derivative of g. Well, look what f is. It's negative. So doesn't g have to be decreasing? And then look what f is. It's positive. So doesn't g have to be increasing? Okay? So that's how we answer that. Then C says, identify any extrema of g. All right, extreme values occur at critical numbers. Critical numbers are where the derivative equals 0 or does not exist. Do we have a couple of places where the derivative equals 0? All right, the derivative equals 0 right there, and right there, and right there. We got it does not exist at 0. Well, that's not an extreme value, right? At 4, right, at this one, at 4, our derivative changes from negative to positive, so our function g changes from decreasing to increasing, which means we have a relative minimum. So at 4, and the value of g at 4 is -8, we already found it, it's a relative minimum. All right, then we have another extreme value at 8. What kind is that? If the derivative is positive and then goes to 0, our function was increasing, so we've got a relative max. And I actually called it an absolute max. If you call it relative max, I'm really happy. Do you know why it's an absolute max? Because that's where it ends. Nothing else happens after that. So we had a decreasing function, so no maximums down here while the function's decreasing. Then it was an increasing function, increase, stop. Well, if it was increasing up until it stopped, that's got to be the absolute maximum value. That's right. That's right. Wait. We're not done. Because the graph stops. So it's got to be closed. Now, you need to do part D. You can do that. But look what all we did in that one problem. We did the fundamental theorem of calculus. We did geometry. We did the first derivative test. We didn't write it out, but we did, didn't we? We knew the relationship between a derivative being negative and positive with increasing and decreasing. That question asks you almost everything theoretical you know about calculus so far. And there's your assignment. 291, 43, 44, 46 through 49, 60, 66 A and B, 67 through 74, 87 through 92.